Friday we were talking about what this symbol meant. So if I go square root of 5, that is a symbol for a different number, and the number that it is different, or that is a symbol for, is this one. Okay? Now, encapsulated in this symbol is also an operation of what this number really means. This number, if I multiply it 2 times, by itself 2 times, it's going to give me that number there. Okay? So that's what we kind of talked about. We did a couple demonstrations of that. Now that number is rounded a little bit, so I might not get exactly 5, because to be honest, we don't know if that's a 7 or not. Okay? Because an irrational number. So every radical we have, except for perfect squares. So perfect squares are 0, 1, 4, 9, 16, 25, 36. Okay, those types of numbers. Those terminate. Okay, because the square root of like 16 is 4.0. Okay, every other square root is irrational, meaning it goes on forever without repeating or ending, kind of like pi does, right? Okay. So when I say that this gets rounded to 7, I don't really know if it should be 7 and the number after it is lower than 5, or if the number after this highlighted thing is actually greater than 5, and this should actually be a 6. Okay, because Desmos is going to round this appropriately per the number that is behind it, and we don't know what that is. So that's why we got what we call a rounding error here. Okay, the more decimal places we go out, the less rounding error we have. But if I put like 16, let's go 49 instead. 49, that terminates to 7, right? So 7 times 7, does that give you 49? Yeah. Okay. But the idea is all of our square roots are going to be irrational unless that number right there is a perfect square. Okay. Questions on that? Now we also could talk about, we're not going to a whole lot, but that number right there, so that's, I'm going to put that 5 in there again. You still see that 2.23 number. That right there is saying the square root. Okay. If it's not written, if that 2 is not written, then we anticipate that it means that they are implying that it's the square root. So it should be a 2. So if it's just looking like that, then we're still saying it's a square root. But we could have a cube root. Okay, which a cube root is now basically that number out front. We call it an index. But basically it tells you how many times you need to multiply this thing by itself to get that thing. Okay, so I'll take that number, multiply it by itself 3 times. And because of rounding error, we don't get exactly 5, but hopefully that convinces you that that would be 5. Does that make sense? That number right there can become anything we want it to be. Okay, if I want it to be 12, then that's the number I need to multiply by itself 12 times so that I get 5. Is that okay with everybody? Okay. How do I use repetitive multiplication? What can I do if I raise that to a 12? That raising something to a power is repetitive multiplication, right? So square roots in the power of 2. That's weird. Square roots in the power of 2. Take this and raise the power of 2. They undo each other. They are in what we call inverses to one another. Okay. So the reason we talk about that is because we need to be able to use square roots in this upcoming section. Also, one other thing. If I take the square root of, let's say, 16, it's 4. Okay? But let's say I take What number can I multiply by itself 2 times to get 16? 4. Or what other number can I multiply by itself to get 16? 4 is one of them. Yeah, but that's not a number. So 8 times 2 is not one number multiplied by itself. So it would be 8 times 8 or 2 times 2.
Okay, so 1 times.
No? No? What's a negative times a negative?
Positive, so negative 4.
So negative 4 will also work. So when we take the square, when we introduce a square root, okay, because remember, we're asking the question, this is a symbol. Where'd it go? This is a symbol for another number that I multiply by itself to get 16. Positive 4 does it. But negative 4 times negative 4 also does. There's actually 2 answers there. Okay? And that's something that we have to talk about as we progress through today's stuff. Okay? And that negative 1 is one that people forget a lot. Okay? So, our goal, remember what we're trying to do here. We're trying to figure out where does our parabola cross the x-axis. Okay? Where does the parabola cross the x-axis? Remember, this is going to be, we'll probably talk about this all week long. Okay? And we're going to go through a series of different styles of parabolas in order to kind of, by the end of the week, have all parabolas be able to find their x-intercepts. Okay? So, the first thing, all of these today that we're going to see are going to be of the form y equals ax squared plus c. So there is no b term. Does that make sense? Okay, we've normally seen ax squared plus bx plus c. Now there's no bx. If there is no bx, this is the easiest way of dealing with finding x-intercepts. Okay. Step 1 says isolate the ax squared term by either adding or subtracting c from both sides. Okay. So this y value, because we want to cross the x-axis. The x-axis is when y is 0. So that the equation will change into that. And then we will try to get ax squared by itself. So subtract c from both sides. If there is an a term that is not 1, we will divide everything by that a. Okay? The third step says solve for x by taking the square root of both sides. And taking the square root of a number produces 2 results. One will be positive, one will be negative for that reason we just talked about. And then step 4, we'll check our answers using substitution and or graphing with Desmos. Okay? So, this question here would actually be eventually, if y equals x squared minus 4, find the x-intercepts. Okay? Well, if I'm going to do that, then I'm going to make the y become 0, because an x-intercept is when y is 0. Y equals 0 is a different name for the x-axis. Okay? X-intercepts are where your graph crosses the x-axis. So, we turn this into x squared minus 4 equals 0. The first step up there said add or subtract your c term from both sides, so that you can isolate x squared. So what's my c term here? Okay, so I'm going to add that to both sides. Okay, so this is how you solve what we call quadratic equations. Okay, I don't know why it disappeared. Sorry. So when everything we've worked on so far in our high school math classes has been probably solving a linear equation. You have your steps of trying to get all your x's on one side and all your constants on the other side. This is now starting the investigation. How do I solve nonlinear equations? Okay, things that are not lines. So that's the first step. Okay. Now the second step says if your a value is not 1, then you divide everything by it. Because our goal is to be able, when we take the square root eventually, we want to take the square root of x squared. We don't want to take the square root of like 2x squared or 5x squared or anything like that. We just want 1x squared. We've already got that, so we kind of skip that step in this problem. So we've got, right now it says step 3, solve for x by taking the square root of both sides. So if I take the square root of x squared, take the square root of x squared, and then I'll take the square root of 4. Okay? Remember what this is right here. Okay? The square root of x squared is a symbol, that is a symbol for the number that I multiply by itself 2 times to get x squared. Okay? When I say the number, I'm talking about, in this case, the variable number, right? Okay? So what can I multiply by itself 2 times as a variable? So what letter would I multiply by itself 2 times to get x squared? I would multiply x times x to get x squared. So when I take the square root of x squared, that's just going to give me x. And that was the idea that I said that square roots and powers of 2 are inverses of one another. They undo each other. They cancel each other out. Okay? So left-hand side gives me x. Now, the right-hand side, what's the square root of 4? What number can I multiply by itself 2 times to get 4? 2. And negative 2. Okay? So plus or minus 2. Okay? Whenever you put in the square root, there's going to be 2 results, plus or minus. You got to remember that. Now, let's talk about what that just did for us. Okay? We're going to bring up a graph here. If I graph x squared minus 4, and I have the line y equals 0, okay, which is that blue line. If I go look at where these two things intersect, do they intersect at an x value of negative 2 and an x value of positive 2? And that's exactly the information that we get by hand that is then modeled in the graph. Is that right? Okay. Do we already know how to find the vertex? By taking opposite of b over 2a, right? So opposite, so b here is 0. Okay. So if I go vertex x equals opposite b over 2a, so that's going to give me 0 over 2, which is just 0. And if I plug that back into here, I get the y value to be negative 4, right? So my vertex says 0, negative 4. Think about this. My vertex says 0, negative 4. I've got that point at negative 2, 0. I got that point 2, 0. Is that enough to graph? 3 points is enough to graph parabola, right? Okay. So that's kind of the goal here of solving these equations to find the x-intercepts, because generally the x-intercepts are going to be 2 points that we can, and I say generally, sometimes it's different, but most times there'll be 2 points that we can graph along with the vertex, and then that'll be enough to graph the entire function. Something to think about here real quick, just an added feature. Isn't this here x equals 0? Is that the axis of symmetry? That green line? Axis of symmetry, right? Is this intercept, which is a length of 2 from that green line, the same length as that one? That makes sense? So every single one of your parabolas that you draw, the x-intercepts are going to be equally spaced from your axis of symmetry. So if I were to give you like a times x squared plus b times x plus c, create a slider here. Let's say that a is 2. Let's go b is negative. Let's go negative 5. And let's say c is negative 2. So if we had, let's say this quadratic right there, okay? The axis of symmetry is going to be at x equals 1.25. Okay? I'm going to ask for the x-intercepts here. So this is just trying to show you, I'm not doing any calculations here, just trying to show you the relationships. So this thing here, thank you much. So this thing here is the axis of symmetry, right? Point D and point C, sorry, point C and point B, those are x-intercepts. If I go D to C, that's 1.600781105. Okay, if I go from D to B, do you see it's the same distance? Those two numbers the same? Okay, and that's the case on every single parabola you're ever going to come across. Okay, and obviously here we see it with the -2 and +2. All right, let's do this next one. What are you going to do first? Add 75.
Square equals 75 square root.
Not yet.
So then you divide by 2.
Yes.
Then you have 2x equals 25 and you square root of 25 and x equals 5.
Okay. So divide both sides by 3. And it gives me x squared equals 25. Then I said square root that. Square root of x squared is?
Wait, what?
The square root of x squared
Oh, x.
is just x. And the square root of 25?
Positive, negative.
Positive, negative. So where's this thing cross the x-axis? 5 and -5. If we graph this, so we're looking now at 3x squared minus 75. Okay, it's a very, very kind of elongated parabola down here to -75. But if I look at the x-intercepts, that point's -5, that point's +5. Are they both still 5 units from the axis of symmetry? Okay, so the next one. Okay, so the next one, so all the other ones were set equal to 0 already, right? Okay, this one is not, but it doesn't matter. You're still trying to get x squared by itself. That's the end goal, get x squared by itself.
So then you would add 14 to both sides.
Okay.
And then they do x squared over 16 and it equals 16. And then you would square root that.
Yep. So I get that.
And then x equals 4. Well, square rooting x, you get x, and then square rooting 16 you get 4.
Okay. And it should be plus or minus, right?
Yeah.
Okay.
So
Now,
if we don't put the plus-
go ahead.
If we don't put the plus or minus on there, will that get us missing off?
Wow.
Because there's two answers, and you would only be provided you one.
But what if you knew that I knew that we were doing?
What if you knew that I knew that?
So then-
That'd be far-fetched, that I would know that you would know something.
I know that
Wait.
you know that.
'Cause I know you.
I know that he knows you know.
So on the homework, we have to put like +4, -4.
It will probably,
There's a little sign.
yeah, there'll either be a sign that you can hit, the plus or minus,
Why don't you tell us that?
or the directions will say type both answers in separated by a comma. Or it'll ask you to type in because the x-intercept is actually the 0.40 and negative 40. So it might actually type in the order pair of these.
Alright, so then it'd be like that number, then 0, then the next number.
Okay, so let's investigate this graphically real quick. Remember what we're really doing when we solve or we write an equation or solve an equation? We are trying to determine where the two sides cross each other. All right, so if we go look at like x squared minus 14 and ask where does that equal to? Okay, what we're asking on the left-hand side, let's look at this. So the original question was x squared minus 14 equals 2, right? So all I did is I graphed the left-hand side and I graph the right-hand side. And what we'd be looking for is where those things intersect. If I look at where they intersect, do they intersect at an x value of negative 4 and an x value of 4? Does that make sense? So this is the original problem being asked. Where does this line of y equal 2 and the curve of x squared minus 14 cross? What is the x value where they cross? We don't like doing that. So what makes it easier is actually to take this line of y equals 2 and make it become the line y equals 0. Take this line or this curve here of x squared minus 14 and actually make it the line x squared minus 16, or the curve x squared minus 16. So we keep those things balanced. So this in the yellow one, we keep them balanced by saying, okay, now let's look at x squared minus 16, and where does that equal, or where does that cross y equals 0? So now we're asking where does the red curve and the blue line cross? What is the x value for those? Is it negative 4 and positive 4 still? That make sense? So what we're trying to answer the question over here in white. Okay? We're trying to answer this question. But the answers to this question are encapsulated or wrapped up in the answers to this question. Okay? And this one is easier for us algebraically to do. Okay? And they're doing the same thing or they maintain equality because I'm allowed to add or subtract the same thing from both sides, right? Okay? Let's do this one. Dude. Add 10 to both sides. So I get 2/3.
And then you, hold on, wait. So yeah, you have to divide the 2/3 on both sides.
Okay.
Is 59 against 59?
Yeah, x
Yes.
squared 15.
So x squared will equal 50. So you can't. So you guys have probably and I've tried to fight this for probably 13 years because I've been teaching here. Is that for some reason you guys have been taught early on that no matter what that number out front is, you're going to divide by it. Okay. But dividing by a fraction is identical to multiplying by its reciprocal. And division itself is the same as multiplying by reciprocal. And I think so if I asked you take 10 and divide it by 2/3, that's hard to envision. But if I tell you to take 2/3 and multiply it by 3/2, okay? And I multiply fractions at 6 over 6 in this case, right? And that gives me my 1 that I want. So I'm gonna come over here and multiply this by 3/2. And 10 is still a fraction, so 10 over 1. And if I multiply straight across the top, what's 10 times 3? 30. What's 1 times 2 straight across the bottom? What's 30 divided by 2? There's your 15. Okay? And that's easier than trying to think 10 divided by 2/3. And even people that grab their calculator and type that in, potentially because they missed parentheses and that sort of thing, could get that wrong. Okay? So I think multiplying by the reciprocal is easier when it's a fraction as your a value. So now I take the square root, right? So here's my question. What number can I take and multiply by itself so that I get 15? Multiply by itself though. So that means I take 1 times 1. Let's go with this. So 1 times 1 is 1, right? 2 times 2, 2 times 2 is 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. I just jumped over the 15 I was looking for, right? So it's not 3 and it's not 4. It's got to be in between there, right? So in this case, 15 is not what we call a perfect square. A perfect square is a whole number that when we take the square root of it, we generate a whole number still. Okay? So this is not, so I'm just going to rewrite this as plus or minus radical 15. And if you get your calculator out, then you can actually find that. Oh, so hard in a math class to use a calculator.
No, listen, come here. It's not even working. Oh, he literally wants it not working.
That is the value, okay? Now, this keeps going on. Okay, it keeps going on forever. So, in a lot of practices, okay, instead of writing it as 3.8729833346, they're either going to tell you round to a specific decimal place, round to 10th place, round to 100th place, 1000th place, 10,000th place, whatever. Or they might just say, leave it like this. Leave it as radical 15, okay? Because this is a symbol for the exact value. If I round this, I no longer have the exact value, right? So the idea is, and there's, with measurements, finding distances and that sort of thing, radicals are very important, okay? If I want to find the distance between 2 points in a plane on the xy axis, we basically use the distance formula, which is the Pythagorean theorem, which uses square roots, okay? So I want to find the distance between 2 things, I use square roots. So here's the thing. If I'm working for NASA, and I'm trying to send a probe to Mars, which involves a lot of distances, right? Should I use rounded values?
Probably not.
Probably not, okay? Because I need to be very, very precise. If I use rounded values, there's going to be issues, okay? If I'm going to Lowe's and I need lumber to make a deck out back of my house, do I need to go to Lowe's and tell the guy working, hey, I need radical 15 feet of some yellow pine?
That'd be pretty funny.
That's what I would say.
And he's going to tell me to go to Menards, right? Okay, so the idea here is that when we're using radicals, the context that we use them in might dictate whether we leave them alone as radical 15 as the exact value, or if we put them in decimal version in round. Okay.
I like that one.
You didn't help me with my calculator.
What's it doing?
Really?
Well, whenever she tries to square root something that comes up to domain error, I think she's going to calculate something.
Nah, look. Okay, I bring up that right away. Bring that there.
What if it's a girl?
Okay, so put a decimal after it.
What? So I think put a decimal after it.
Do that. It might like 0.
Why do you have that?
So your I'm sorry. Your calculator. So some of your calculators, guys, will do.
Do you not see the 15? And Marl's in there.
Yeah, why does it need a decimal?
Once he got hit, he shrunk.
Okay, so as we move into further into working with radicals, the practice will eventually be to leave them as exact values. So we will want to leave it eventually like this, okay? So some of your calculators, I don't know if this one will do it, some of your calculators are programmed to leave when you hit, so Jenna's was when I typed in radical 15, where mine says 3.87, hers still said radical 15, okay? Because of the nature of us, what we want to do later with these things, we would prefer the radical 15 over this. But if for any reason your calculator does that, and you want it to give you the decimal, all you gotta do is either most calculators, you just gotta put a decimal point in the radicand. That's called a radicand, R-A-D-I-C-A-N-D. And then put a 0, or it might just have to be the decimal, and then it will give you the decimal version. Okay. So basically what it's doing is your calculator's program, if user types in whole number, return answer using whole number. If user inputs number using decimal, return answer with decimal. Does that make sense? That feature on your calculator, Jenna, will be awesome for you later on, because what we want to do later on, so let's say radical 45. Our goal later on, well, to be, I'm going to delete that. Well, to be simplify that. Simplify radical 45. So we know 2/4. We can simplify 2/4 to what? 1/2, right? So radicals are the same way. Radicals, when we simplify a radical, we want to remove the perfect square that is inside 45. What perfect square is inside 45 as a factor? What number can I multiply by something to get 45? And one of those numbers being a perfect square. Huh?
5,
Okay, so 5 times
8. You said 45?
45, yeah.
9.
So 5 times 9. So 9 is a perfect square, right? So if I go, so what's the square root of 9?
3.
3. So the square root of 9 times then that radical 5, that gives me the same 6.7 number. Okay? Now, that process, so radical 45 and 3 radical 5, those are equivalent symbols for the same number, right? Okay? We like this 3 radical 5 much better than radical 45, much like we like 1/2 better than 2/4. So Jenna, take your calculator, type in radical 45, and it gives you that right there, right?
That is not.
So that's nice. Now, if you wanted the 6.7 number, then you'd have to put a decimal on the 45, or after the 5, and then 3 radical 5.
That's nice. Are we gonna use that in all this year?
Yeah. Okay, so let's do this next one.
Alright, you got it. Let's go.
I
Ella can do it.
What do I do?
Wait, are we talking about the x squared one?
X squared plus 4?
No, no.
Yep.
Okay. So you have to subtract 4 and then squared, and it's x squared equals -4
You sound scared when you're saying that.
Okay, so trick question.
It's the negative.
Trick question.
They do, Mom.
No, you did everything right. And what happens here, though, is got to remember what square root does. What number can I multiply by its, because I'm trying to get the -4, right? What number can I multiply by itself to get -4?
You can't.
Why not?
Because everything counts itself, so it's gonna be fine.
Okay, so if we're saying positive 2, it'd be 2 times 2, so we can do positive 4, not -4, right? And if I try -2, -2 times -2
It's gonna be.
is still positive 4, right? So there is no number that you can multiply by itself to get -4. Okay, now, there is something that we do, and I hesitate to talk about this, but we might as well. There was a guy a long time ago named Leonard Euler. Okay? Leonard Euler. What he was trying to do is this exact question. Okay? Instead of 4, he was putting a 1 here. Okay? He was saying, okay, what number can I multiply by itself so that I get -1? And there's no answer to that, right? So Leonard Euler invented a number. Okay? And you got to think about what is mathematics? Do we invent things in mathematics, or do we discover things in mathematics?
Discover them.
Okay?
Okay, but how did we get the number?
Okay, so
So I can just.
we go back to like the early ages of having a necessity for numbers. What would have been maybe one of the main reasons for numbers long time ago? Thousands and thousands of years ago.
To count.
To count what?
Food.
Okay, so if I go to the market, okay, I've
Wait, a long time
got
ago?
3 chickens. I'm going to trade 3 chickens for 1 cow, right?
Oh, okay.
Okay,
Well,
so
totally.
so we had a need for numbers like that. Okay, early on, okay, as a civilization. Did I need maybe halves at that point? Let's say first day of the market. I'm trading live animals. Do I need halves? No. But then we start figuring out, hey, we can kill these animals and chop them up, and I can sell now 2.5 goats for 5 chickens, right?
Zebras.
So then we had the need for fractions. Okay? So we got to argue, are those inventions or are those things out there that were hidden and we just uncover them? Okay? You know, the Romans, they didn't have a number for, you guys know what Roman numerals are, right?
Yeah.
Anybody know what the Roman numeral for 0 is?
0.
There isn't one.
There isn't one. They didn't have 0. Okay? So the Greeks, they did not have square roots. Okay, so one of the issues that the Greeks had early on with their human curiosity was, if I take a square and I try to find the length of the diagonal, okay, so take a square and find that distance right there. Okay, they could measure it. Okay, they could take their measuring devices and do that, but they could not mathematically calculate it. Does anybody know what that distance is? If this is like, say, 3 and that's 3, does anybody know what that distance is?
I can't.
Talked about it in geometry.
Something N? Is that what it was? Is it 3N?
No, it's n radical 2, so it's going to be n is 3. So that distance is 3 radical 2. The Greeks couldn't do that because they didn't have square roots. They didn't have radicals. Okay. So Euler, same time, he's like, well, I can't do this because I don't have the numbers to do this. So this guy, he actually invented this, and he brought in, if I take the square root of a negative number, and he defined it by a square root of -1, that is the same thing as what we call I. Okay? Which is what we refer to as kind of like what Austin has in regards to friends. Okay? This is called an imaginary number. His friends being imaginary.
I got no one.
Okay? Wow. I would probably stick with telling people that I have imaginary friends before I tell them I'm friends with Noah.
You know what number I invented?
What? Shut up. So that we're not going to dig any deeper into this right now. It will be a concept later on. But right now, basically here we say no real solution.
Oh my god.
Okay? And the word real doesn't mean that there's not a solution that doesn't exist. Like a fake solution, something like that. The real refers to the number line, the x-axis. Basically tells us if there's no real number on the x-axis, okay? Think about what x squared plus 4 looks like, guys. X squared plus 4. Remember, x squared looks like that, right? What's plus 4 do to that parabola? Adds 4 to every y value. Does that parabola cross the x-axis? This image right here, the x-axis is that line right there, right? Does that parabola cross it? No. So this work right here, when we say no real solution, tells us, it doesn't tell, because we want to know where we cross the x-axis. That's the hope that all these problems generate. Sometimes they don't. Okay? If you might think this work was futile, it was worthless because I don't get the answers. It does provide me some information. At least tells me I don't cross the x-axis. Okay?
No answer is still an answer.
No answer is still an answer, yes. Okay. So we'll stop there for today.
All right, man.